So it's been 2 weeks, so we're back again. And today we have Professor Bhaskar Dutta. He's a professor of economics at Ashoka University and the University of Warwick. His research interests include cooperative game theory, mechanism design, formation of groups and networks, social choice, development economics. Many of us here have been taught by him. Sanjeev is here in some way
Hi,
or the other.
Bhaskar.
Hi,
He's had
Sanjeev.
long association with the with the Indian Statistical Institute, where he taught from 1979 to 2002. He has been a visiting professor of several universities. He has been a recipient of the Mahalanobis Award of the Indian Econometric Society, has been a president of Social Choice and Welfare, fellow of the Econometric Society, Game Theory Society, and Society for Advancement of Economic Theory. He's been a chair of the Standing Committee for India and South Asia, as well as a member of the Council of the Econometric Society. He has been a member of he has been managing editor of Social Choice and Welfare, and currently is advisory editor of Games and Economic Behavior. He got his PhD from the University of Calcutta and his master's and PhD in economics from the University of Delhi. With that, I will give the floor to Professor Bhaskar Dutta. He's going to talk about defense and interception in networks. He will take questions as we go. Yes.
Thank you. Just one correction. My PhD was from the University of Delhi, not University of Calcutta. Not that it matters.
Yeah, the bachelor's was from the bachelor's is from University of Calcutta.
The writing is correct in the bio sketch, but I must have said it wrong.
Okay. So this is a joint work with Francis and Kolyan. Both of them have spoken earlier in this series. It's still work in progress, and it's been work in progress for an inordinately long time. Our only excuse is that, well, we happen to be on 3 continents. So this is actually a topic or area which has been fairly well studied in operations research, not so much by economists or game theorists. So these are models, the network interdiction models. They analyze the monitoring and stopping of an adversary's activity on a network. By the way, when I said that it's not being worked very much by game theorists, one exception is a paper by Sanjeev Goyal and Marcin Zywinski. They have actually worked on somewhat similar problems. So what are phenomena that we want to model? Well, it could be counterterrorism. It could be the interception of contraband and illegal items such as drugs. It could also be infectious disease control, though in our model, I mean, this doesn't really fit into our model, because in our model, the adversary, both parties are intelligent players. I'm going to skip this in the interest of saving time. So as I mentioned, ours is a full-blown game theoretic model. The basic features of the model are the following. So I'm going to discuss 2 different versions. I'm going to spend more time on the decentralized model. Here, so we have a network, an exogenously given network. Each node is a player in the decentralized model. There's one distinguished player that we will refer to as 0. Think of 0 as being the attacker. It's, for instance, the person, the player who sends the contraband drugs to targets in the network. These nodes have possibly different values to the attacker and the node itself, though this is not really going to play a role in our particular model. The attacker endogenously chooses our target node T, as well as the path through the network through the target. Each node is going to choose an inspection strategy. So we are, as I said, we're going to focus mainly on a non-cooperative model where each node is a separate player. We're going to show existence of equilibrium. It's going to be a Nash equilibrium. The model will have and it's going to be a unique equilibrium. And then finally, towards the end, I'm going to compare sort of limited comparison with a cooperative model where some central agency chooses the inspection strategies of all the nodes.
So one question.
Yeah.
So will every point on the path to the terminal node will be destroyed or not? Only the last one for a selected path.
Can I take this question later? It's going to be
Yeah,
clear.
yeah.
So the n+1 players, 0, and then there are n nodes other than player 0. So player 0, the sender, owns one indivisible unit of some bad item, let's say a packet of drugs, a bomb, whatever, something like that. The possible targets are players 1 to n. And these n+ nodes are vertices of an exogenous network G. Whether it's undirected or directed is not really going to play a major role in the analysis. So if 0i, so I remember is the sender, if 0i is in the network, is a link in the graph G, then we are going to say that I is an entry point for the attacker. The value of each target I is some number bi, and that's less than 1. This is, you can think of bi being less than 1 as a normalization. So the strategies are the following. Player 0 chooses a path P with the terminal node I. So the target node is I, and P is a path in the given exogenous network. So this is a pure strategy. A mixed strategy is going to be probability distribution over paths. Each I, that is each of the possible targets, can choose an level of inspection or a detection level xi at cost xi squared by 2. Of course, bi is less than 1, so xi is also going to be between 0 and 1. If the object I, sorry, this should be not I, if the object reaches node I, then it is detected with probability xi. The payoffs are the following, and that answers Siddhartha's question. If the object reaches the target and is undetected, then the sender gets a payoff of bi, whereas the target, player I, gets a payoff of minus bi, that's the cost to him, plus he also loses the cost of inspection. So the total cost is minus bi minus xi squared by 2. On the other hand, if the attack is unsuccessful or J is simply not targeted, then the sender gets 0. So there's no cost of sending the object. But everyone has to incur, anyone who spent something on the inspection, he or she incurs that cost. So it's I minus xi squared by 2 is the cost to I, and sender gets 0. So the strategies are chosen simultaneously. And so the focus is going to be on Nash equilibrium. Any questions at this point? This is the description of the game.
So I mean, the node, any arbitrary node on the graph knows that it is along a path chosen. I mean, is that important?
These are the strategies are chosen simultaneously. So
Yes.
knowing in equilibrium, you know what's happening in the equilibrium. So you choose one of the nodes, you choose an inspection level, xi. You immediately incur a cost of xi squared by 2. And then if you happen to be the target, and it reaches, the object reaches you, so one of your predecessors on the path may also be choosing a positive inspection level. So then the object has to pass that node. Okay? So there's a positive problem. If J is your predecessor, J has chosen Xj, then with probability 1 minus Xj, conditional on reaching J, the object will pass through J. Okay. Does that answer your question?
Yes, sir.
Bhaskar, there is another question.
Mm-hmm.
It says, what is the action space of player I? Sorry if I missed the description.
So the nodes, the target, the potential targets, they are choosing a level between 0 and, let's say, 0 and 1. That's the inspection level. And if it chooses half, you pay half squared by 2. If you choose xi, you pay xi by 2. I'm sorry. I mean, does that answer your question? This is I strategy, to choose an inspection level xi. So let me go through an example. To a large extent, I'm going to spend 2 or 3 minutes on the example because the example tells us a lot about what's actually going on in the model. So this is the exogenously given graph. This is the graph. So 0, 1, 1, 2, 1, 3, 2, 4. These are the links in the graph. The values of these nodes are B1 is 0.4, B2 is 0.1, B3 is 0.5, and B4 is 0.3. So here's a description of the graph, okay, and the values of the B's are given here. So what's a candidate equilibrium? Okay. Now, a couple of things that immediately are obvious. For instance, it's clear that nodes 2 and 4 are never going to be attacked. Why? Well, because in order to reach, let's say, in order to reach 2, the attacker has to go through 1. It has to pass undetected through 1. Now, if it is successful in passing through 1, then if it attacks 1, it gets 0.4. So there is no reason why the attacker would pass through 1 and attack either 2 or 3, because the value 2 or 4, because the values of 2 and 4 are smaller than the value at 1. So from here, we immediately see that along the attack path, even if the player is choosing, the attacker is choosing a mixed strategy, the only nodes which are possibly in the support must be a sequence of increasing nodes with sequence of increasing BI values.
Sir?
Sorry?
Hello. So what if the probability of being detected at node 1 is extremely high and that of node 2 is very low? So then he can skip
But
1 and go to...
Remember, one, so first, another fact which is clear is that if one is not, if one in the candidate equilibrium, if one is not attacked, then one is not going to place any defense. Okay, so in that case, the attacker can go through 2, passing undetected at 1. But again, that can't be an equilibrium either, because in order to come to 2, the attacker has to pass through 1. So suppose you tell me, well, he actually chooses 2 and he doesn't choose 1. That's the equilibrium. That can't be the equilibrium, because he can then deviate and attack 1, which is supposed to be undefended.
All right, sir.
So what if node 4 had B4 as 0.5?
B4 as 0.5?
I mean,
well,
will anything change from what you said?
Yes, because then 4 could be attacked.
Yeah, so you stated a monotonicity property. Could you restate that?
Yeah.
Like
So,
that increasing thing.
So suppose B4 is 0.5. Let me change this to 0.5. Let's keep B2 at 0.1. Okay, and B1 is 0.4. Essentially, then I could say that, well, actually what matters, effectively I can actually drop node 2 from the analysis.
Okay.
Because the attacker is not going to attack node 2. 2 knows that, so 2 is not going to defend. Why incur a cost if you are not under attack? So it's as if 1 and 4 are directly connected. Okay, if 4 has a value of 0.5. But what I wanted to illustrate with the original values is that it's clear that nodes 2 and 4 cannot be in the support of the attacker's strategy. 1 and 3 can be. And we now have to derive the equilibrium attack probabilities on 1 and 3 and the defense strategies of 1 and 3. Okay. So this is essentially what I've said. So you attack one with probability P1, 3 with the residual probability. 2 and 4 are going to be 0. P2 and P4 are going to be 0. And in fact, these are going to be the values, but we need to determine these. And it's very easy, but let me just go through the mechanisms. So let's check what are going to be the necessary conditions. Okay. First, if B1 and B3 are both being attacked, this is a mixed strategy, so the expected utility to the attacker has to be equal. If he attacks B1, then X1 is the defense. So he passes, he is undetected at 1 with probability 1 minus X1. So this is what he gets by attacking 1. By attacking 3, first he has to pass through X1, through 1. So that happens with probability 1 minus X1. Then 3 also defends with probability 1 minus X3. So this is the equilibrium condition, which simplifies to X3 is going to be equal to B3 minus B1 by B3, which is equal to 0.2. X1 minimizes this. This is one's loss function. And whereas X3 is going to minimize this. So, and P1, P3 is equal to 1 minus P1. So we use these two equations, then this is what you get. And now you can go back and find that X1 is going to be P1, B1. So P1 is 0.5, B1 was whatever, 0.3. So that gives you the value of P1.
Excuse me, can you see how to determine X1?
Do I?
The X1,
so X1 minimizes this. So
X1 the payoff is decreasing in X1. So is that typo?
Sorry?
It seems the payoff is decreasing in X1.
Whose payoff?
X1, play one.
No. I mean, decreasing because this is the loss function.
Okay. Okay, sure. Sorry.
That's why he's minimizing that. So what are possible?
Bhaskar, there should be a minus term before the.
Oh, I'm sorry. Yeah, you're right.
Okay.
I'm sorry.
Okay.
Okay.
Thanks, indeed. This is the total. This is the cost. So basically, you can check that there can't be any deviations because we have taken into account the fact that the attacker is indifferent between attacking 1 and 3. Both have to be attacked because if 1 is not attacked, if only 3 is attacked, then that cannot be an equilibrium, which comes here. So suppose 1 is not attacked in equilibrium, then the entire weight is on 3, and then that will give us, the attacker will get 0.25, but by stopping at 1, he would get 0.3. So 1 has also got to be attacked. Okay. So let me now go to the, I wanted to spend some time on this example because this illustrates some of the main features or characteristics of the model. So what is a proof of existence in the general model? Well, that follows from the Debrog-Glicksberg-Fan theorem. The strategy sets are sets of probability distributions, finite set of paths in G for 0, and 0, 1 for the n nodes. So these are compact and convex sets. Payoff for I is continuous in S minus I, and it's also linear in Si. So that ensures that this theorem ensures an equilibrium in actual pure strategies. But for 0, since we're taking the strategies to be probability distributions over paths, essentially pure strategy here means probability distribution over paths. So existence is more or less trivial. More interesting result is the uniqueness and characterization theorem. I'm going to spend, so to get uniqueness, we have to assume that no pair of nodes have equal value. So Bi is not equal to Bj for all Ij. Then we can show that there is a unique equilibrium in the general model. But for heuristic purposes, I'm going to show this for what I'm calling simple trees. So basically a simple tree means this. So from the node 0, first it's a tree. And from the node 0, you basically have a set of straight lines. Okay. But again, I want to emphasize that this is just for heuristic purposes. The paper, when it is written, if it is written, we'll have a full proof. We actually have the proof, but we're still polishing the paper. Okay. So let the set E be the set of entry points. In this diagram, the entry points are 1, 2, and 3. And each I is going to be the head of a line Li. On each line, assume that Bij is less than Bij plus 1. That is, you have an increasing sequence of values. This is without loss of generality, because if two nodes don't satisfy this requirement, then drop the node which comes later. So if Bij plus 1 is less than Bij, then Bij plus 1 is never in the support of the attack distribution. And so it can be dropped from the analysis. Let I0 be the first node to be attacked in Li. We can we can actually determine I0. I0 need not be this node, for instance, because even if 1, 0 and 1, 1 have this increasing sequence property, increasing value property, if 1, 0 has, if the value, the B at this point is very low compared to 1, 1, then 0 may actually want to skip 1, 0 and attack 1, 1. But we can determine this. We can on the line, we can actually determine what's going to be the support from the B values. But I won't go into that. And let Ik be the node on this line, on the line Li, which is the highest value. It's a terminal node of this increasing sequence. So then L star is going to be the support of the attack strategy. Some Li stars may be empty, but let's ignore that. Now let alpha I be the probability that the object has reached I, but has not been detected by node I. So alpha I is going to depend upon the xj's of all the predecessor nodes of I on the path, as well as on xi. It's going to be of the term 1 minus xj1 minus xj2, etc., up to 1 minus xi. Let x star be the equilibrium response vector of the nodes. Then on the line Li star, alpha I0 is going to be 1 minus xi star 0. And then alpha Ik plus 1 is going to be 1 minus x star Ik plus 1 times alpha Ik. Because alpha Ik is the probability that it has escaped up to the node Ik. Then it arrives at Ik plus 1. Ik plus 1 itself will also check with probability x star Ik plus 1. So this is the probability that it can pass through Ik plus 1 undetected. Now again, the attacker must get the same expected utility from attacking any two nodes. And this gives us this equation. Alpha Ik Bik is equal to alpha Ik plus 1 Bik plus 1. But we also know that alpha Ik plus 1 from the previous equation is equal to this term. And that therefore gives us the equilibrium value of xi star k plus 1. I'm going to use this equation 1 will play a role several times in what follows. Let now P star be the equilibrium attack probability. Sorry, again, there's a typo. So then node IK's expected loss I'm sorry, again, this is the plus, is given by this. Alpha I minus 1 is equal to 1, and that's just a notation because it always comes to the first node. So that gives us xi star k plus 1 is this. Xi star is equal to simply the probability that the first node is attacked times the value of the node. That's equation 3. Using these equations, we can, equation 4 expresses pi star k as a function of pi star I0. That is, along any line, the probability that Ik is attacked is some increasing function of the probability that the first node, the I0 node, is attacked. And this is what I've written here. So pi I is an increasing, every pi I is an increasing function, strictly increasing function. Now let's look at the first nodes to be attacked along the different lines. Okay. So again, use the fact that the attacker has to be indifferent between all these nodes. That gives us this equation. So you can fix some I in E and then express every P star J0 as a function of the Pi star I0. And again, the P star J0 is going to be an increasing function of the P star I0. And now we have this, in a sense, establishes uniqueness because all the sum of the probabilities have to add up to 1. And you have all these increasing functions. So fix the Pi star I0. Then the P star J0 is every P star J0 is an increasing function. Every P star Ik is an increasing function of P star J0 and hence of P star I0. So other than P star I0, every other probability is an increasing function of P star I0 and hence because the probabilities add up to 1, you have uniqueness.
And here you are also using the fact that the BIs are distinct, right?
The BIs are, sorry?
Distinct, I mean, for the uniqueness?
No, well.
Or no?
No, not really. Here I'm not. Am I using it here? I'm actually going to use it in the second part, for the general model, not for the tree so much.
I mean, it could not happen that some probability adds up to some two probabilities add up, but how they are distributed, that doesn't matter.
Not for the trees. Oh. Not here, but I need it for the general model where the graph need not be a tree.
Oh.
I need the distinctness of the B values for the general model, for uniqueness on the general model. So this is going to be a unique Nash equilibrium. It could be a pure strategy equilibrium. For it to be a pure strategy equilibrium, this condition has to be satisfied. There has to be some node I such that Bi times 1 minus Bi is greater than or equal to Bj for every other location. If this condition is satisfied, this is a pure strategy equilibrium because if I is attacked with probability 1, he will detect Xi will be equal to Bi, and so this will be the expected utility. And this inequality ensures that you don't want to deviate. Now, one feature of this equilibrium is that it's not the case that the attacker always wants to attack those nodes which have high value. That is, it doesn't want to focus its attack only on nodes which have high value. To see this, let's take the simplest possible example. So you have a two nodes graph, three nodes, 0 and then nodes 1 and 2. These are the values. And suppose it's 0 is connected to both 1 and 2. Now, if the sender attacks 2 directly, with probability 1 that is, then his payoff is going to be 2 by 9. This cannot be an equilibrium because he's then better off deviating and attacking 1. So he has to attack both the nodes. In the equilibrium, it has to involve attacking both nodes. These are the probabilities, and then the payoff is going to be 6 by 25, which is greater by 2 by 9. And essentially, the idea here is that by increasing the support of the attack distribution, you are because you're attacking the big node with a lower probability than you would if you focused on it. That reduces the defense, the level of detection, the detection inspection level of the big node. So you're more likely to be able to mount a successful attack.
Yeah.
In the process, you also attack nodes which have lower value, but it turns out to be worthwhile to do that. So, does existence of many paths to the same target, to what extent does it complicate matters? That is, in the proof of uniqueness. It turns out that it doesn't, and it doesn't for a very simple reason. Even if the graph G is not a tree, if it's not a tree, then there can be multiple paths to the same target node. However, we can show that given the values, the BI values, and of course the graph, there must be a single path of attack which we can identify to each possible target. There are two steps in showing this, that there must be a single path of attack. First, take any I, suppose this is not true, take any target node I, and suppose there are two attack paths, let's say R and R path, R and R prime, leading to this, leading to I. Then it must be the case that the sequence of predecessor targets on R and R prime are identical. Why? Well, because suppose J and K are distinct, are immediate predecessors, and they're distinct, then because the attacker is indifferent between attacking J and I, this is true. This has to be true. But the attacker is also indifferent between attacking K and I, sorry, J and I. So the second inequality, second equality also has to be true, which means that Bk is equal to Bj. But we have ruled that out. And again, to go back to Siddhartha's question, this is where we use the fact that Bk, that all the values are distinct. Otherwise, you could have had one target being attacked through different paths, and that can complicate matters. In fact, you could have an equilibrium. You could have multiple equilibria because in one case you attack through two different paths. In the other case, you attack maybe through only one path, and so on.
Is there a general genericity argument here? I mean, in the sense that you're using two paths. Wondering.
We have in some sense imposed the genericity argument by saying that no two values bi and bj, no two values are identical. We have explicitly.
I mean, sir, is it fair to?
I think I mentioned it somewhere.
Yeah, no, I'm just wondering whether the argument is.
Yeah, here.
Yeah, okay.
So that always allows you to rank paths, right? However arbitrary the graph is, you can always figure out which paths to
One
use.
Question.
Yeah, go ahead. Have I lost you?
Hello.
Hello. Can you hear me? Can you hear me?
Yeah, I think Siddharth is trying to ask a question. Go ahead, Siddharth.
We seem to have lost Siddharth.
Yeah, I think you should go on, Bhaskar. Yeah.
Sudipto, you also had a question, I think.
No, so I was saying that because you have the distinct values, that always allows you to rank the paths of attack.
Rank meaning? I'm not sure what I mean. Because
I mean sort of choose the attack strategy.
Yes. So I was going to come to that.
Okay.
And it could be that you have two paths. They have the same predecessors, but which one do you choose? Which path do you choose? And we can identify that, because otherwise it could be that you have multiple equilibrium. So suppose the two paths R and R prime lead to the same target with distinct predecessors J and K, but you are not using one of them to go to I. But we know that alpha J Bj is equal to alpha K Bk. Again, because since J and K are attacked, the attacker has to get the same expected payoff. But then Bj not equal to Bk implies alpha J is not equal to alpha K. So then the attacker would choose to attack through J if alpha J is greater than alpha K. Why? Well, because if you want to attack I with the highest probability of success, so remember, if J is the predecessor of I, then the probability that you actually reach I is alpha J. And if you attack through J, the probability of success of reaching I, if you attack through K, is alpha K. So you want to attack through alpha J if this inequality is satisfied. And given this equation, which must be true, since Bj is not equal to Bk, we can also rank the alphas. So the attack will be through the node of lower value. So now we are very close to trees. We are in trees, in fact, because the only complication of the graph not being a tree is that you can have multiple paths to the same target node. But we have resolved that problem. The only difference between a general tree and the simple tree that I used to provide a proof is that, for instance, you could have things like this. You could have forks like this. This actually doesn't create any problem at all. So I'm going to skip this.
Sir, I had one question.
Go ahead.
So the quadratic nature of the cost is implying certain linear conditions on the first order conditions, right? How important it is that, I mean, it seems to be important. Is it true? I mean, could it be general if you lose quadraticity?
This is what we have. Some of the results can go through. Essentially, what we started off with a model where proof of existence will go through. We don't need that. We don't need this quadratic cost.
Yes.
It's just need bounded. You just need a compact strategy sets. Proof of unique existence goes through. We also want to, at the end of the day, we also want to do some comparative statics. It turns out that the model is not very easy to work with. So we are trying to simplify the model as much as possible, hence the use of quadratic functions. So again, uniqueness will also go through. What will not be true, where we'll have a problem is in comparative statics, which I'm not actually, we don't have any worthwhile results to present today, but we hope to get there. Okay, very briefly, the last issue that I want to take up is comparing a cooperative scenario with the non-cooperative model. So in the cooperative scenario, what I mean by this is that suppose there's a central agency which coordinates defense strategies. Remember, so far, the individual nodes are choosing their defense, how much to defend, how much to spend on defense. I'm not going to restrict attention to lines because that's what we have so far. And again, without loss of generality, let's assume that the line is such that you have an increasing sequence of the B values. As I've remarked earlier, this is without loss of generality. Because again, if for some pair of nodes, if this is reversed, then simply drop the lower node from the analysis. So now, think of D as being the central agency. It's now a two-person game between 0 and D, and it's not a zero-sum game actually. I heard someone whispering zero-sum. It's not a zero-sum game because of the inspection cost. The inspection cost does not enter zeros payoff in any way. It's borne by D. So, and here I've got the sign right. It's a plus sign. So D's objective is to minimize this expression given equation 5. And then the first order condition, that's simple. I won't go through these.
Now, I have a question, Bhaskar.
Go ahead.
Yeah. So at this stage, when we have the central designer, is the network structure given or the designer also forming the network?
No. The network structure is exogenous.
Okay.
I want to compare the cooperative scenario with the non-cooperative scenario. So in any case, think of whatever, these are different cities. They apprehend that some bad guy is sending drugs. They want to have a coordinated defense strategy, but the paths connecting the cities are given. They don't control that.
So just to understand the motivation for this, so is it the case that the security investments, the XIs, is there a kind of a clean theoretical Is there a clean strategic structure to the game? Are they sort of strategic complements?
The Xi's are going to be right, because if I precedes J, then if I put some investment on I, I'm also helping J.
So there will be substitutes. And so I guess it will depend on whether I and J have a sequential, they are following in sequence, or they are actually on independent paths of it.
Yeah, so if they're on independent paths, then I and J, what I doesn't affect J. But if I precedes J in the graph, then I's defense, the more I defends, the better it is for J. But that is also true in the non-cooperative version.
Yeah, I was thinking about I was just wondering whether it's the case that there's too much defense in the non-cooperative version. There's excess defense.
It's going to be the other way around.
Oh, I see. Okay.
That's what we're going to show.
Okay.
Except maybe in the first node. In the first node, there'll be more. In the last node, so remember, I'm talking about a line. So node 1 is going to invest more in the cooperative case. Node n is going to invest the same amount, and 2 to n minus 1 will invest less in the cooperative case. That's the result.
Oh, I see. Okay.
I'm going to discuss that.
Okay.
Okay, so these are going to be the first order conditions. These are the first order conditions. And it's clear that this has to be true. Yi has to be greater than or equal to yi plus 1. Why? Well, suppose yi plus 1 is greater than yi. Now reverse the two. Then the total cost doesn't change. But now, if I was under attack, if I is in the support, then because you're now defending I with greater level of resource, that helps I. It doesn't, and I plus 1 is indifferent, because the defense on I plus 1 is 1 minus yi times 1 minus yi plus 1. So if you interchange yi and yi plus 1, it doesn't affect I plus 1. It doesn't affect total cost. The only advantage is that I benefits from a higher level of defense. So it must be the case that yi is greater than or equal to yi plus 1. Okay. Another difference between the cooperative model and the non-cooperative model is that in the non-cooperative model, of course, if you are not under attack, if you're not in the support of the attacker's equilibrium strategy, then you don't defend yourself. But here you are going to, because of this condition, yi greater than or equal to yi plus 1. I'm going to sidestep this issue. In fact, in my answer to Sanjeev, I was. This is going to be again, we can show that on the line, there's a unique equilibrium. We can actually give a sufficient condition for full support. And now I'm going to give a comparison of the expected loss in the cooperative and the non-cooperative case under the condition that the entire line is under attack, both in the cooperative as well as in the non-cooperative case. So, in a sense, the sufficient conditions are satisfied. So this is in fact the condition. In the cooperative case, all nodes will be attacked if this is true. this condition is true. But let me now just compare the two. So remember that in the non-cooperative case, every I is minimizing this expression. So this gives xi star is equal to alpha I minus 1 pi bi. If you now substitute this back in the Li function, then Li will turn out to be this xi star 1 minus xi star 2. And Li is therefore increasing in xi star. In the cooperative case, these will be the values. Y1 will be equal to B1, which is of course greater than X1. So Y1 is the cooperative level, X1 is the non-cooperative level. So the first node is going to invest more in the cooperative case. All the other nodes will invest the same. They will invest the same because the Xi's and the Yi's we can derive from the attacker's condition, equilibrium condition. Remember, Xi was equal to 1 minus Bi minus 1 by Bi. Similarly, Yi will also be equal to that. So these come only from the Bi values. So these are determined from the Bi values. The only defense element which is not, which doesn't come directly from the Bi's is only the first node. But we know actually what these are. So from the first order condition in the cooperative case, we can derive these expressions. And then Mn will be this. So this is the loss for the last node. The loss for the last node is exactly the same as the loss for the last node in the non-cooperative case. But for the other nodes, 2 to n minus 1, Mi will actually be less than xi minus xi squared by 2, which remember was the loss for nodes 2 to n minus 1. And I'm sorry, this is n minus 1. So for I equal to 2 to n minus 1, Mi is less than Li. Everyone, all these nodes do better under cooperation. Oops. I'm sorry, this is replete with mistakes. M1 is greater than L1, and the last node, Mn is equal to Ln. So what we want to, so these are the results I wanted to present. We have some limited comparative static results for the non-cooperative case. I've skipped those because currently they're all very partial results. We hope to be able to improve on them very soon. So basically what we're doing, the kind of comparative static results we're looking at is comparing a line versus a star. In particular, from a star, suppose you move one node and you put it at the end of a line, then what happens to its utility or its loss? If you change one value, don't change the node, don't change the graph, but change the value of one, the BI value of one node, then what happens? So we have some limited results of this kind, but nothing more than that. Okay, so I think it's 7:30 and I'll stop here. Happy to take questions.
Thank you, Bhaskar. I think, yeah, we can still do some questions. People want to stick around. If If you want to leave, you can. Officially, we're done with 1 hour, but we're happy to take questions and have a chat.
So, I was sort of wondering if you've thought of it. Yes, because you gave examples on network interdiction, and I'm trying to. This is the world. The world of your model is one where, if I'm not being attacked, I don't mind you using my territory. There's no cost to me.
Mm-hmm. In fact,
just trying to understand that a bit. Okay.
No, in fact, Sanjeev, in this model, if I'm not using a detection strategy, if you pass through, you're the attacker, you have sent a packet of drugs through me, I don't even get to know whether you've done that.
Yeah. Mm-hmm. Mm-hmm. But there must be a social value, right? I mean, so there's no individual value in my investing if you're not attacking me. But there could be a social value in my defending myself, even if I'm not being attacked, right?
Yeah. So that's sort of the cooperative model. So
yeah, solution.
Okay.
Bhaskar, there was a question in the chat earlier from Shubhro, which was saying that instead of, I mean, I guess in contrast to the cooperative solution, what would happen if player 0 could sort of collude with some of the players along the path and pay them off?
Well, here...
And I said to wait till the end because that's not part of the model. So now that we are at the end.
Here, if suppose you are my predecessor, so if I'm not attacking you in the non-cooperative version, if I'm not attacking you, this is my answer to Sanjeev, then you are not going to defend yourself, right? So I am passing through you, your node. I don't have to pay you off. I just have to tell you that you're not under attack. And that's in the equilibrium, you know that. So positive.
I would recommend, there's a really very interesting paper by Melissa Dell on the Mexican cartels. I think it's in the AER, and it's quite, I think it's just very interesting to look at that. It's about how people route the drugs.
Okay, I will take a look. You said AER?
So it's a paper by Melissa Dell, I think, and it's about the routing of drugs through Mexico. And the idea is you want to get to the American border and you could use different routes. And the routes you use depend on the political leaning of the mayors of the different cities or the different, I think you might find it interesting, actually.
Yeah, we'll definitely take a look.
It's mostly an empirical paper, but it's about optimal routing by drug lords.
No, we will certainly take a look. That seems very well.
I find it interesting. Yeah.
And there was also a few years back, Myrna had a student. Myrna Wooders has a student who was looking at that routing BADs, pollution and things like that.
Paper, but I don't think that has any direct intersection or any direct bearing with this. But I've seen that paper. So we started with a much more difficult problem. We started with one where everyone's level, so everyone has all the nodes have a level of competence of CI, and CI is uniformly distributed between 0, 1. And that's private information. The non-cooperative model, it's exactly the same, because in fact, that's why the quadratic version and the uniform distribution give exactly the same result. But we didn't know how to model the cooperative part, because if the CIs are private information, then that's a very hard problem. So then we switched to this.
Can I ask a question about the unique part of the equilibrium? It seems quite unexpected result. So what kind of property give you the uniqueness in your model? I guess I'm just want to see what are the driving forces. Because usually in each complicated model, we don't expect uniqueness of equilibrium. So, and also you don't have a construction of the equilibrium in the general cases.
Well, in the general case, we don't have a construction of the equilibrium.
Right. So that's why I'm quite surprised about the unique part of your results.
Well, remember, we have to assume that the BIs are distinct.
But that's a generic condition, so I'm fine with that. But even yeah.
Otherwise, there's nothing else that is, because essentially what the genericity argument allows us to do is to show that we can identify the path along which any target is going to be attacked, and it's going to be a unique path. So once you have that, and of course, the attacker is never going to use walks. Why do you want to loop around? You are subjecting yourself to multiple inspections. So but once we can identify the path and we know it's a single path, then basically we are able to convert a general graph essentially to a tree. And then the proof that I gave you for simple trees, that's very close to the proof for any arbitrary tree. So forks, etc., those don't really complicate matters.
Mm-hmm.
I can take from an entry node, I can think of it as a line. I can the probability with which the first node is attacked, that's hard to determine. But given that all the succeeding nodes, the probability of attack is an increasing function, strictly increasing function. In fact, we know what it is. It's I had the expression in the slides, the BIs and the BI minus ones, etc.
Mm-hmm.
But once you have that, then the rest is easy. And then you can pick any one entry node. Suppose that's under attack. So that's one of these I0s. All the other J0s have to be increasing functions of the I0, because again, the attacker has to be indifferent between attacking any two nodes in the support. And that's essentially what we need.
Right, but maybe I missed the page about the assumption on the graph. Do you assume directly the graph or indirectly? Somehow I missed that page.
Well, I mean, you start from a particular node, right? The 0, the attacker. So, and the attacker has to come to the target. So it doesn't matter whether it's you're only going to move in one direction. You're not going to move from the target to the attacker.
I see.
So it could be, I mean, in principle, you could move from the target to the attacker, but that direction of movement is irrelevant. So you can assume it's a directed graph. It doesn't make any difference.
Mm-hmm.
And between any two nodes, you could move in either direction. Again, that doesn't matter.
Very nice.
Oh, thank you, Sandeep.
Very nice.
But it's, as I said, it's a bit thin right now, and the comparative statics are turning out to be not very easy to do.
But I think the trick to convert the general graph into one where you can do the tree analysis, that's the clever trick.
Actually, the way when we write the paper, then we'll just give it, the proof will be directly on general graph, because that's the way that it's written in our notes, except that we first started with a tree, then we moved to general graphs. But now when we write the paper, it will be in terms of general graph. Here it's for expositional purposes. I thought the tree was easier to work with.
Thank you very much.
Have you thought of the
problem for a nice talk?
So initially, when you started presenting the paper, I thought that 0 is outside. So 0 is, it doesn't matter, right?
0 has to enter the graph at some points.
Okay, yeah.
One or more points. Because otherwise he can't reach the target.
Well, it matters, right? Because he could actually enter at the target.
We allow for that possibility. I mean, we are saying give us any exogenous graph. Maybe it's a complete graph for all you know. So include 0.
And then you have a trivial equilibrium.
It will have a trivial equilibrium. You'll attack directly. If you want to attack target I, if I is in the support, you'll attack directly. If you can. So we are not making any assumption on the graph. It can be any graph.
So is it possible that you sometimes prefer to have an indirect route to attack?
No. Because you are multiplying the rounds of detection. The level. So if I can attack you directly, but I attack Sudipto and then you, I mean, if I'm not attacking Sudipto, then whether I go through Sudipto to you or you directly is the same. Because Sudipto is defend himself. But if he is being attacked, then he defends himself. So then it makes sense to, if I can attack you directly, it makes sense to attack you directly or deviate and attack you directly. The equilibrium can never involve me attacking you through Sudipto, but not attacking you directly, if I can.
So this setting, is it true that...
No, because the reason is the following. When you take your defense strategy into account, you take into account the possibility that the fact that Sudipto is defending too.
Sure.
Sorry, go ahead. You had a question.
No, I was curious whether is there a simple comparative static that you take a graph and you fix the graph and now you have O or 0 and then you add some links.
Mm-hmm.
Did you have a result of that kind? Or?
We don't have any comparative static results actually, of this kind actually, no. But come again, can you repeat your question?
Well, I was just wondering whether there's some sort of there's some very simple intuition that if I add links, I can access people more efficiently.
Mm-hmm.
So I should be better off.
You being the attacker.
Yeah.
Yes, because I mean, it's almost a reveal preference argument, right? Because you can always do the original set of links. If you prefer not to do that, then it must be because you're better off.
So then, of course, one could ask questions about these guys who are, potential targets, whether they want to. But maybe it's a different paper. What kind of network they want to have?
Mm-hmm.
Maybe there's a very simple.
I suppose the reason why we were modeling it this way is because even what you're modeling, if it's the drug trafficking, then the set of potential paths that comes from a phenomenon. It exists. I mean, these are cities.
Sure.
And links between them. To stop drug trafficking, you're not going to cut links. I mean, sort of. That's the.
No, because in the I think in some of these applications, the question is posed along the following lines that you want to connect up nodes because that generates value. But when you connect up nodes, of course, these connections can be used to route the attack.
Yeah.
But it seems in your setting, you would probably want to have a minimal. You probably want to have a tree.
We probably want to have a tree. That's right.
And then you may want to locate the high value guys. Yeah, I don't know. Yeah.
Further away.
Probably, yeah.
That's one kind of comparative static that we want to do actually.
Yeah. Interesting. Mm-hmm.
Okay. Thank you, Bhaskar.
Thank you.
Thank you for the talk.
Great talk. Yes, thank you. Malik, did you want to announce the? It's kind of late. You should have announced earlier, I think.
Yeah, you were there?
Yeah.
I don't think any of the junior people are there, so the purpose will be lost.
Yeah, I think so. I'm just opening this one also.
Yeah. So let's do it next time at the beginning, because I think now there is the people have, for whom this is intended are not there.
Yeah, a lot of people are missing.
Yeah. So students and so on have mostly left.
So thank you, Malik and Sudipto and.
No, great, Bhaskar. Thank you. It was. I had heard the earlier version of this.
I don't
that's
think
a different paper actually. No, that's a different paper.
No, the very initial version of this I had heard in the US. I think at George Washington, when Sumit had invited you. I think at one point. No, or that was the block paper. That was the other paper, the rumors paper.
I think hide and seek, maybe.
Yeah, the hide and seek paper, yeah.
No, I think that was a rumors paper which we didn't. That was with Kollan Chatterjee and we didn't do anything. We stopped.
Oh.
We haven't written that book because they want to know enough results. But this I'm presenting. Well, I presented this in Brussels, one version of it last year. I think you may have talked to Francis about it, but I don't think you've seen it.
Yeah, that's possible.
Very interesting talk.
Okay, thank you. Thank you.
Thank you. Yes.
So keep me informed about the
Yeah, so next week I can tell you. So next week it's actually Yusuf Chan Masitlioglu. So he's going to do
he's
some
with
kind of,
us.
yeah.
He's with us today.
Yeah, so Yusuf Chan is probably going to do some kind
He
of
works behavioral economics, right?
no, social choice, stochastic choice. So he's that part of the Turkish group in Maryland. So Yusuf Chan and Erkut Ozbey and all these guys.
Where is he?
Maryland, University of
Yeah.
Maryland.
I think he also works on behavioral economics.
Yeah, he does. I mean, yeah. So there, some of those models have so revealed preference, stochastic choice, these kind of ideas, and sometimes they have behavioral assumptions, but basically axiomatic choice problems.
Okay, if I'm not doing it, so next week I'm starting teaching in Warwick, and obviously difference going to be.
So it's in 2 weeks. So yeah, so it is towards the end of this. It will be 2 Tuesdays from now, or maybe Wednesday. I have to check.
So Wednesdays I can't attend because Wednesday is my Warwick seminar. I mean, we have Warwick seminar on Wednesdays, but Tuesdays my teaching starts from the 5th of November.
Okay.
And it's going to be in the evenings because.
So, okay.
Or after.
So I think it's
late afternoon.
Okay. So we'll keep you posted. It's Yusuf Chan, and then I think after that is Matt.
Yes.
Okay. Okay. Thank you. And
okay. Yes.
Stay safe.
Yes. All right, everyone. Bye.
Thank you all.
Bye. Bye.
Hi, Yusuf. I didn't know that you were here.
Nice to talk to you. Yeah. Bye.
Yeah.
Bye.